So welcome back, everybody, and I hope you're doing fine. Can everybody hear me well here? So all fine? Okay. So what I want to do today is a kind of first the standard messages. Well, first of all, thanks to Julie for stepping in on Monday. Julie's fantastic, isn't she? We all agree on that. And what we're going to do today is quickly to remind you about some of the things which are relevant for the homework, which comes now. I don't know if you had time to look at it, but you can find both Julie's recording and handwritten notes from Monday. But then we also have a video, or two videos actually, which deal with exercises 2 and 3. And as we announced last week, this harmonic oscillator serves as a kind of stepping stone towards a more interesting case. Now, before we move to the interesting case, which is actually to look at elliptical orbits and Kepler's laws, I just wanted to come with a small digression. So I have the questions by many of you. Why do we care about scaling the equations? And this is something which sounds a little bit strange. Why don't we plug in the physical constants? So one of the reasons why we scale the equations is that it simplifies the mathematics if we want to find the analytical solutions, but it also simplifies the numerics. You get rid of different constants, but then you have to be careful with units. So scaling differential equations and equations in general is actually something which can lead to actually pretty bad results. So I have an example here of a really bad result of wrong scaling of the equations. And you may not have heard of this case, but let me show it to you. So often we switch to different units. So this is a NASA mistake. So in September 99, they lost an expedition basically to Mars. Nobody died, fortunately. But this was because NASA used the metric systems as units. And Lockheed, which produced the this kind of climate orbit, as it's called, they used the imperial system. So in the codes, in the codes, there was a conversion which was done wrongly. So the price tag for this was something like $125 million for having lost this thing close to Mars, actually. So this is one of the typical examples which can go wrong when you're scaling equations and you're forgetting about the right units. Unfortunately, there are many worse cases like this where human lives have been lost. So scaling equations properly and keeping track of that when you write codes, or even when you solve things analytically, is something which is extremely important. It simplifies for us, it simplifies the equations. Sometimes you may not make them dimensionless, like when we did with the Earth-Sun case. And as you're going to see in the next midterm, when we're going to look at Jupiter, Earth, and Sun, and also the solar system, then it's convenient to scale the equations, because else you have all these constants you need to carry with you. And in that case, we scale the equations to some new type of units, which was astronomical units, the distance between the Earth and the Sun, and number of years as of a time unit. So keeping track of different units is extremely important, because you are going to encounter analytical calculations and numerical calculations where we need to keep an eye on what kind of units are being used and how the equations have been scaled. Because normally we simplify the equations so that we can reuse the same codes. Then you have to multiply with the right units. And in this case, between Lockheed and NASA, one used metric and the other one used imperial units, and it just went wrong. So that's just one case which didn't lead to people dying, but there have been cases with a fatal outcome, actually. Too many cases, actually. And if you're interested, there's actually a book here, which was written by a good friend of mine before he passed away, on scaling of differential equations. So if you're interested in this topic and a deeper motivation for why you do this, and this topic sounds like a very boring case, but it's extremely important when you're going to solve equations, and then you want to put in the right physical units. Okay, so what I'm going to spend the rest of the day is essentially a standard whiteboard, blackboard exercise, and we're going to derive elliptical orbits. And this is one of the cases where we can solve equations analytically with a gravitational force. And we're going to go through some tricks. And at the end, we are going to end up with a very simple equation for the radius as a function of the angle. And this equation here is an equation which we can, by certain conditions, can give us a circle. It can give us elliptical motion, parabolic, and hyperbolic motion. And these are the things which are of interest for us physically. So by going to the polar coordinates, instead of running everything in Cartesian coordinates, we have a way to extract some physics understanding, which we normally would not have gotten if we looked at the system in Cartesian coordinates. So the mathematical exercise today is more about us using this transformation to polar coordinates and finding an analytical expression which is going to give us elliptical orbits. And that's pretty nice. So this is, I say, from my point of view, this is one of the more fun cases with this course, actually, where you can get analytical expressions and understand why the planets move as they do. Okay, so let's go through the mathematics here. Any questions so far? So let's switch to the whiteboard. And let us quickly remind ourselves about some of the things which we have seen. So when we have internal forces, what we found is that L is a constant. So it's conserved. We chose something which we call the center of mass frame. That means that we just translated the system so that the center of mass position is equal to 0. What we had then is that when we dealt with x, y, z for the relative position for r equal r1 minus r2. So x, y, and z here are the coordinates of the relative position in Cartesian coordinates. So what we found then is that we could reduce the problem to just x and y, because angular momentum is conserved. So, and then what we did was simply to switch to polar coordinates. So remember now that x goes from minus infinity to plus infinity, and y is also defined from minus infinity to plus infinity, whereas r, which we switch to, is defined from 0 to infinity, and the angle phi is defined from 0 to 2 pi. And we know then that x is equal to r times cosine phi, and y is equal to r times sine of phi. So this is the kind of setting which we now are living in when we want to solve equations. Yeah, a question. I just have to. Let me see if I can do it with this one. Can you hear now better? Is that better? Excellent. So I have this tendency of mumbling after some time. Sorry for that. Now you're hearing well, right? Good. Excellent. Okay, so what we have then, when we look at the equations which we ended up solving, so we have an equation for the angular velocity, which we wrote like this phi dot, and that was given by the angular momentum divided by the reduced mass of r squared, and mu is simply the mass of the first object times the mass of the second one divided by the total mass. And then finally, what we have now is an equation for the radial acceleration, which is given by So we have times mu here. So this is the radial acceleration times mu. So that's the radial force. So we have the force in the radial coordinates plus L squared divided by mu times r cubed. So this is the equation of motion, which we now want to solve. And what we're going to do today is to find the analytical solution of that equation. Now, another piece of information which we had from last time is that the energy in this new coordinate system is given by the potential as a function of r. So in our case, this could be the harmonic oscillator in exercise 2 and 3 of this coming homework, or it could be the gravitational force or any other type of force. So later in some of the exercises, you will replace the gravitational force with another type of force. So what we have now is the kinetic energy. So the kinetic energy was given by the derivative. So this is the velocity, the radial velocity. And then we have the radius again, times the angular velocity. So this is actually times the angular velocity squared. So this was the expression for the kinetic energy. So potential energy plus kinetic energy. Now, what is common to do then, as we said last time, is to define an effective potential, which in a sense is artificial, but what we are doing now is to bake in the kinetic energy term into parts of the kinetic energy term into the potential energy term and define an effective potential. So what we're going to do now is to use this relation here, in here, and then we are going to rewrite the equation in terms of a kinetic energy term, which depends only on the radial velocity, plus one term, which is V of r, as before, but then we have plus 1/2. And when we now use the relation which we have for phi dot, this one here, and plug it in here, we can actually rewrite this equation as an L squared divided by 2 mu times r cubed. This defines an effective potential. And the angular momentum, which is now the way the system is rotating, is going to define what's normally called a centrifugal barrier. So when we now analyze the problem in this new coordinate system, our potential is now something which we can define in terms of an effective potential. And then we can try to analyze what happens with the system if we now think of only the radial degrees of freedom. If you also look at this equation here, you see that the energy is a function of the radius only, the absolute value of the radius. So because it depends, the equation here depends only on r. So it means now that what we have is simply an energy, and we are going to need this equation a little bit later when we're going to interpret the orbits. So when we make a plot here, we would get something like this for the gravitational force. Oops, for the gravitational force. So if we have a V of r, which is equal to some minus alpha divided by r here, this is the potential we're plotting. And then we can look at different situations like here. And in the videos and in this material on exercise 2 and 3 for this homework, what we found is that in this position here are the second derivative. That means the radial acceleration is 0. And that leads to a constant velocity. And what we can infer from that one is, since this is in 2 dimensions with x and y, this is going to be a circular motion. So that's a circular motion. Now, what you could also say is that, okay, let me place myself here. So I have, so the energy here, E of r, at this minimum, we are going to have kinetic energy because the radial velocity is non-zero. And there will be some potential energy. If we now place ourselves at another position here, we may have an energy here which is going to lead to a type of motion which is going to, where the object is going to oscillate back and forth between this point and this point. So this one is going to give us elliptical orbits. And this is what we're going to show today. And then on Friday, I'm going to sneak in some 10, 15 minutes where we're going to derive parabolic and hyperbolic orbits. And they're going to correspond to different energies of the system. So the elliptical motion and the circular motion, they are going to correspond to what we called bound motion. So you're bound to move around an origin. And the origin in this case is, for instance, going to be the sun. We're going to think of the sun as so massive that we can approximate the system with the sun being at rest and all the planets orbiting around the sun, and then having the new origin defined by where the sun is located. And that means that in this case, the different planets are going to move in a bounded orbit, in the same orbit. If we now look at the energies which correspond to positive potential energies, we are going to get motion which is unbounded. So the object will be pulled in, and then it will be deflected and leave away from the object which it is approaching. And we are going to look at these different cases gradually now. But let's now go through the solution of the equation of interest. So what we want to solve, actually we are going to show that we can solve this equation here, the second derivative. So this is the force in the radial direction. So we have the radial acceleration plus L squared divided by mu times R cubed. And for a potential, like the gravitational potential, which leads to, if we have a potential like this, which is minus alpha divided by R, that leads to a force with radial degrees of freedom, which is equal minus alpha divided by R squared. And we are going to show now that this has an analytical solution. So we want R as function of the angle phi. And this is the things which we're going to deal with large fraction of the lecture here as function of the angle phi. So we need some tricks or some mathematics here. So the first trick which we are going to use is actually to define, and this is something you will see in many of these solutions of equations like the one you have here. You're going to define a new function, which is 1 over R. So depending on the type of forces you have, you may attempt to introduce another type of variable. So this means that when we now are calculating this d of R as a function of phi, of d phi, this is going to be equal, when we now just use the standard derivation rules, 1 over u squared times du of d of phi. So I hope that sounds okay. So these are just some basic definitions which we need when we now are going to find the analytical solution here. The second trick, which we are going to use, it's actually useful to have seen these things, because if you, in some kind of occasion, may end up with having a differential equation like this, you may remember this trick and then try to implement it and see if you can find an analytical solution. So these analytical solutions, if we can find them, they're worth gold, because they really allow us to analyze the system in perhaps an easier way than when we just solve things in Cartesian coordinates. So what we need to do now is to rewrite the time derivative, because we are taking the derivative of the radius, or R. So we need to rewrite that in terms of, and we want to rewrite it in terms of d phi here. So I want a solution in terms of phi. And we know how to solve phi as soon as we have the expression for r. Okay, so now comes some gymnastics, some exercising here. So we know that this can be rewritten as d phi dt of d phi. And this is something which we would simply rewrite as phi dot times d phi. So we have a differential operator here. Now, what we need to remind ourselves of is that phi dot is L divided by mu over r squared. So I can plug that one in. And then we simply have L divided by mu over r squared of d phi. So that's the first step which we need. Then, if we now look at the expression, we have defined this function u, which is 1 over r. So we can rewrite this d dt as L divided by mu, and then we have u squared of d phi. So why do I do this? Now, we do this because we need the next thing. So we have the radial velocity, which is given in terms of the derivative of r with respect to time, dr dt. This is the quantity which we called an r dot here. So remember again that no vectors here. We're just looking at the radial dependence, which is given by the square root of x squared plus y squared. And this is now, when we now plug it in, we can show that this is same as L times u divided by mu. And then I have a d of d phi. And then I can put in r, or I can put in 1 over u, since this is the new function I want to solve with respect to. And if I do that, if I take the derivative, we know that this actually simplifies, because the derivative of this one with respect to u here is something which is going simply to give us minus 1 over u squared times the derivative of u with respect to phi. So this is going to give us L divided by mu, and then I have a d of u of d of phi. So we need some more manipulations now, because we want the acceleration in terms of phi. So that means that we need to take another derivative with respect to time. We want the second derivative. And so be patient, that we are just going to do some more manipulations here. And then at the end, we are going to see that we end up with an equation which can be solved analytically. It's actually going to look like a harmonic oscillator equation. So let's take a closer look here. So the next thing which we need is obviously the second derivative of d of r dt, which we wrote as r with 2 dots. So this is equal to d of dt of the first derivative with respect to r. So if I do that, what this is L times u squared divided by mu of d phi. And now I need to plug in the derivative with respect to r. So I need to take this expression here and put that one in here, because that is our derivative with respect to time. So I hope you can forgive me my slight laziness here with just pointing an arrow and not rewriting the whole symbol. So if we do that, if we now do the manipulations, what we are going to get, and I'm just going to give you the final answer when you do the manipulations, you're going to get something which is given by minus L squared of u squared. And this is divided, if I take the second derivative, it's given by mu squared. And then I have a d of u of d phi second derivative. Now, this quantity here is now the quantity which is going to be equal to f of R, which is also given by 1 over U, plus, and now I have my term which goes like L. So this is the force now divided by mu. And then this is given by mu squared times R cubed. If you look at this expression which we have here, we would rewrite that one as L squared times U cubed and mu squared. Okay, so if I collect everything, and if I now just rewrite the expression for the force which we have, divide with the F and so on. So we are going to divide the expressions by divide with L squared on both sides and U squared and multiply with the mass. So we are going to get a d of the second derivative of d phi, which is going to be equal to minus, and now we have the force here, F of U, multiplied with mu, divided by L squared times U squared. And what happens now when I divide by L squared, the mass, and also U here, is that I simply get minus U here. So this is a new equation and doesn't look like as if we have gained much, right? But now comes the potential, which we are going to plug in. So we have V of R, which is equal to minus alpha divided by R. This means that our force, F of R, is given by minus alpha divided by R squared, which is the same as minus alpha multiplied with U squared. So if you look at the equation which you end up with then, if we now plug this one back into the expression for the force here, then you see that the U squared term disappears. And I end up with a constant. So my differential equation then looks like as follows. So I get a constant, which is minus alpha. So let me just plug it in here. So this is going to actually be given by plus alpha plus mu times alpha divided by L squared minus U. So let's suppose now that we don't have an external force or a force which acts between the particles. Let's put this one equal to 0. So it's the same as putting alpha equal to 0. Then we have an equation which looks like this. And we've seen that before, haven't we? So anyone remembers what the solution to this equation is? We saw that one with another variable called time when we looked at harmonic oscillations. So if you look at the final equation which we have here, where we put the constant equal to 0, do you remember what kind of solution we may expect then? Let me give you a hint here, because you've seen this one in another disguise. You've seen this one as d of x dt equal to minus omega squared times u times x. This is what we have seen before. So if you put this omega 0 squared equal to 1, this is the same. Yeah, now it rings a bell. Yeah, Leah.
Oh, does it become cosine and sine?
Yeah, cosines and sines. So what we have done now is, by these two tricks, by introducing this 1 over u, we have been able to rewrite the equation in terms of a simple equation which we can solve. So sometimes when somebody says, when you have an equation like this, this is one of these differential equations which you will see again and again in physics. And this is the equation for harmonic oscillations. And that gives you a cosine and sine. So when somebody gives you like that, you don't even need to think, you just say cosine and sine. So here now is to take a complicated
Hey,
equation.
Morton, I think your the Zoom audio is kind of messing up right now for some reason.
Okay. Okay, so is it better now?
Test it out again. Just
So is the audio okay?
okay, yeah, it's better now. It was just being
Okay.
weird for a minute.
Okay, so I'm just going to stay a little bit closer here in case the audio is getting a little bit messy for those of you online. Okay, so if we now look at the solution here, we know that this equation u, when I put these constants equal to 0, this is simply given by a u, which now could be given by a constant cosine of phi plus a new constant d multiplied with sine of phi. And we can compactify this one into something which goes like cosine. And this is something which goes back to what we did with harmonic oscillations, which has a phase shift. So we can always rewrite this equation here by some manipulations. We could also use exponentials if we wanted to. Now, if we now bring back the full equation here, what we could do now is, and I'm going to show you another trick, because we have simply a constant which is added to this function u. The other thing you should keep in mind is that r of phi is actually equal to 1 over u of phi. So you see now the glimpse of the final solution. That's going to be given by a times cosine of this phi minus delta. Now let's add the constant term. So what is common to do then is now to define a term or a function which is given is a function of phi, which is simply given by the solution u of phi, which we found, minus mu of alpha divided by L squared. So when you see a constant like that, you would simply solve the system for another type of variable. So this means that when you plug this one into the differential equation, we know that d, the second derivative with respect to w of d of phi, this is simply going to be equal to minus of this omega. So what that means is that this function omega, when we solve it, that is going to be equal to some constant, let's call this b, times a cosine, and we have a phi minus a new delta, I just use the same name here. And since I have used this definition here of this function, then we can easily find u of phi as this function w plus mu alpha L squared. So what we have then is a constant b times cosine of phi minus delta plus mu of alpha of L squared. Now we can always scale these equations so that this delta is equal to 0, delta to 0. And then we have a solution now of this u of phi, which I'm going to merge into a new constant, which I'm just going to call for a constant c. So I'm going to have a mu of alpha of L squared plus, let's keep this constant b here, of cosine of phi. I can rewrite it as a mu of alpha divided by L squared of 1 plus epsilon. And this epsilon plays an important role now. This is going to be called the eccentricity. So for those of you who have taken a course in astronomy, you have probably encountered this parameter. This parameter plays an important role when we now are going to analyze the type of orbit which we are going to get. So if you now look at what we have here, if we now use this constant. So this is simply equal to B times L squared divided by alpha times mu. So this is a constant which is defined in terms of the physical parameters of the system, the parameters of the gravitational force. So in our case, alpha is going to be given by the gravitational constant times m1 times m2. That's the definition of the parameter alpha for the gravitational force. But you are not confined to look at this as a gravitational force problem. You could think of this as the Coulomb force. In that case, that constant alpha would be given by the charges of the two particles times 1 over the permittivity in vacuum. And then you could solve the same type of problem for two electrons which are interacting with each other, and then ask yourself, what is the solution, the classical solution to the problem? And actually the classical solution to the problem for two electrons will be similar to the gravitational force problem, because the force goes like 1 over r squared. So when you see something like 1 over r squared as a force, the analysis which we are doing here now can actually be applied to other physical systems which are governed by the same type of forces. So just keep that in mind. What you see now is pretty general for potentials which go like 1 over r. They lead to equations which you can solve analytically. They lead to equations where angular momentum is conserved, and you can find an analytical solution. The whole analysis here is something you can transfer to other forces which go like 1 over r squared. And that's pretty neat. Any questions so far? So I wanted to take you with me on this journey here, because there's a lot of nice mathematics which allows us to gain some deeper insight about the physics. And that's what we are after anyway. So if we now continue a little bit, we can now rewrite this equation, and it's common. So there are too many constants here, by the way. So it's common to rewrite everything in terms of a constant C, which is given by L squared divided by mu times alpha. And then we take the inverse here. So remember now that this epsilon is given in terms of B of L squared or alpha of mu. So we can now, if we take the inverse, what we get then is R of phi is given by C divided by 1 plus epsilon of cosine phi. Yeah. So the only thing I did now was take U, which is equal to 1 over R. Because now what I want is actually R. And the only thing I did was first to solve everything without the constants. So when I did it without the constants, I had the solution which is up here. That's the general solution here. And then I simply looked at the solution in terms of another function where I have the constants. And with that, I get a general solution for U, which is given by the term you see here. And when you have that, what you, sorry, just a moment, I lost my, not that one, here we are. So when we do that, we simply need to take 1 over U equal to R with this redefinition of the constants. And then we end up with the final equation, which is given here. So this is your radius, right? R. So remember now that what we have when you make a plot here in terms of X and Y. So your R goes out here, and then you have an angle phi. This is just to quickly remind you about the connection between the Cartesian system and polar coordinates. So if I put epsilon equal to 0, what kind of motion do we get? Circular motion, because the radius is constant, right? So isn't this neat? You can actually look at the solution here, and we now say that this constant epsilon is equal to 0, and then we have circular motion. So let's see how this relates to the energy, because we can link this epsilon to the energy of the system. So that means that you can go back to this graph of the potential energy, and you can look at different energies, and you can infer from that the type of motion you're going to get. So let's do some more, some further analysis of the type of system here. So we see that epsilon 0 is going to lead to circular motion. That's pretty neat. Now, let's now ask ourselves something else here. So can there be min and max values of this radius? Of r of phi. So if you now look at the expression for r, so we said that r of phi is given by this constant c of 1 plus epsilon times a cosine of phi. So if I want to find the minimum of the radius as a function of phi, what would you guys do then to find the minimum possible radius which you can have? Take the derivative. So we require that the derivative of the radius with respect to phi is equal to 0. So we want to find the minimum radius now as a function of phi. So let's do that. So if we now take dr d phi and require that one to be equal to 0, now we have to be a little bit careful here when we look at the analysis. So this one, we just take the standard rules for derivation. So it's going to give us a c times a sine of phi divided by 1 plus epsilon of cosine of phi squared. Now we are now going to assume that epsilon is not equal to 1. This is a special case. So when epsilon is equal to 1, and we're going to see that on Friday, this is going to lead to parabolic motion. But let's now look at the case where epsilon is not equal to 1. So what we can do then is we can simply, because if epsilon is not equal to 1, we see now that we don't run into the problem with a divergence. Because if epsilon is equal to 1 and phi is equal to pi, this becomes 1 minus 1. And then we are into problems. So if we now leave that case of epsilon equal to 1 and simply solve this equation, so that means that we would need a phi, which is either 0 or pi, right? So from the sine function, we can now simply say that, okay, this means that the angle phi has to be either 0, because if the angle phi is 0, sine of 0 is 0. If the angle is pi, sine of pi is 0. So these are the two angles which give us a solution which now points to the minimum or maximum value. So we don't know whether it's a minimum or maximum, right? So what we can say then is that the angle phi is either 0 or phi is equal to pi. So if I put phi equal to 0, what we get then is that r of phi is simply equal to this constant c divided 1 with 1 plus epsilon. If I put phi equal to pi, that means that r of phi is simply equal to c of 1 minus epsilon. So we have assumed that epsilon is different from 1 and that it's also larger than 0. Because when it's 0, then we have circular motion. So which leads to maximum and which leads to minimum with a fixed epsilon? So if you look at these two solutions, which one corresponds to the minimum radius and which to the maximum? Any good choices? Any good selections here? Yeah?
Yeah, the top one is the minimum.
Exactly. So this gives us a minimum radius, and this gives us a maximum radius. So if we now look at a possible plot which we could make, the system which we are going to end up with, so this we are going to call this R min, and this is going to be R max. So when we took the derivative and required that equal to be 0, we didn't know whether we would get a minimum maximum. So if I look at my plot now, what we are going to get, and we are going to see that this epsilon is going to be smaller than 1. And this is something which we are going to derive later. But this means that what we have now, when we look at the potential, we are going to have an R min here. This is this one. Here we know at the bottom here, we know that this corresponds to a circle. So we have the second derivative equal to 0, and we have this epsilon equal to 0. And then we have an R max here. This, what you see here now, is going to lead to elliptical orbits. And this is the next thing which we need to show here. The thing which is interesting, since R of phi is given by this constant C of 1 plus epsilon times cosine phi, we see now that the solution, when we plot the solution, we're going to get a situation which looks like this. So if we put 0 here, we have pi here, and we have 2 pi here. We see now that if we start with the minimum value, then we have a solution like this. So we put a 1 here, and then we have 1 minus epsilon. So we have something which goes like this down to the minimum here, and then it comes back again. So we have a period which is equal to 2 pi. So after 2 pi, it just repeats itself. So this is just us looking at the solution. And so the radius is now going to oscillate back and forth between two values. And as you will see now with some further manipulations, this is going to lead to elliptical orbits. So let's do that as the last point today. And then we're going to pick this up again on Friday a little bit. And then also next Monday, we're going to discuss more the connection between the energies which you see. So what I mentioned now was simply that when you look at this energy plot, I simply said that this corresponds to an epsilon which is smaller than 1 and larger than 0. But I didn't show it to you. Now on Monday, we are going to show it. That starting from the expression for the energy, you can show that the value which it takes, the energy takes, leads to these specific choices of epsilon. And when we have an energy which is going to be equal to 0, that's going to correspond to epsilon equal to 1, and so-called parabolic motion. When epsilon is larger than 1, this is going to lead to hyperbolic motion. So that means that you would have a planet or a comet or whatever, which comes towards the sun. It comes to a minimum distance between the sun, and then it's deflected by the sun, and then it disappears afterwards. So let's look a little bit closer at how we can, from these simple expressions, how can we go from what you see here, this simple expression which we have, where did I put it? This one. If we take this one, how can we show that this leads to elliptical orbits? So that's my last step today. And actually, we are getting close to the end of the time. So I'm going to sneak in, I'm going to steal some 10 minutes from the exercise solution on Friday, and just show you that this actually leads to elliptical orbits. Now, let me also remind you, for solving the exercises, take a look at the lectures which Julie had on Monday. and also the other videos which we put online, which are directly linked with the homework now. And we use the harmonic oscillator as a kind of stepping stones towards the more interesting case. And actually, this harmonic oscillator and polar coordinates is an overkill, because we cannot solve it nicely and analytically as we did in Cartesian coordinates. For the gravitational force, on the other hand, we cannot solve it analytically in Cartesian coordinates, but we can solve it analytically in polar coordinates. Okay, guys, I hope you can see the wood for the trees, because there are many bits and pieces which we're bringing together. But the final expression which we get is so simple, and it's so easy to gain a physics understanding of Kepler's laws by looking at this equation. Okay, guys, thanks for coming. And feel free to hang around if you want to, or if you have other things you want to do. I also have office hours tomorrow at 9 to 10 if you wish to use them. For those of you online, I'm going to stop the recording, and the movie will just be uploaded. George and Julia online, if you wish to continue discussion.